the moon, the human story of Earth's closest world, asleep in class. Welcome or welcome back to Asleep in Class, where we settle into long, quiet lectures about history, science, invention, civilization, and the strange paths of human knowledge. This episode follows the moon, not only as a world of stone and dust, but as one of humanity's oldest companions. It has been a nightlight, a calendar, a sacred sign, a scientific puzzle, a place of human footprints, an archive of solar system history, and now a destination for a new age of exploration. This is a calm journey through the human story of Earth's closest world, before science, night, time, myth, and memory. Long before there were telescopes, rockets, observatories, spacecraft, or astronauts, the moon was already part of human life. It rose over camps, villages, deserts, forests, islands, fields, and cities. It changed shape in a way that anyone could see. It vanished into darkness and returned. It brightened the night enough to guide movement, work, fear, prayer, and imagination. Before people knew what the moon was made of, they knew that it mattered. The moon is close enough to seem intimate and far enough to remain unreachable for most of human history. That combination gave it a special place in human memory. The stars appeared fixed in patterns that changed slowly across the year, but the moon transformed night by night. A thin crescent could become a half-lit disk, then a full round light, then shrink again toward darkness. These phases made the moon one of the most obvious timekeepers in the sky. Many cultures developed calendars that followed lunar cycles or combined lunar months with solar years. A lunar month, measured from one new moon to the next, is roughly 29.5 days. That cycle is not exactly the same as a solar month, and lunar calendars require adjustment if they are meant to stay aligned with the seasons. But the moon gave people a visible rhythm. It allowed time to be counted without written clocks or mechanical instruments. It let communities mark festivals, rituals, travel, hunting, planting, waiting, and return. The moon also shaped the experience of night itself. A full moon over an open landscape can turn darkness into a pale second day. A new moon can make the night deep and uncertain. For people living without electric light, the difference mattered. Moonlight affected travel, labor, ceremony, and danger. It could make paths visible. It could expose movement. It could calm a village or make shadows stranger. Eclipses added drama to this relationship. A lunar eclipse happens when Earth passes between the sun and the moon, casting Earth's shadow across the lunar surface. Today, this can be explained through orbital geometry. But before scientific astronomy, the darkening of the moon could feel like a cosmic event filled with fear, meaning, warning, or sacred power. Many societies told stories about eclipses, and while those stories differed greatly, the emotional force is easy to understand. The familiar light in the night sky suddenly changed in a way that seemed too large to ignore. The moon also became part of myth. It could be a god, a goddess, a spirit, a boat, a mirror, an eye, a rabbit, a hunter, a maiden, a dead ruler, a guide, or a world of beings. Different cultures saw different shapes in its markings and gave those shapes different meanings. The moon could be associated with fertility, death, rebirth, madness, wisdom, time, water, animals, women, kingship, or the dead. It was never only one symbol, because human beings never looked at it from only one world. Even where the moon was not worshipped as a deity, it could still structure life. Its rising and setting affected nights at sea. Its cycle influenced ritual timing. Its light and absence shaped stories of danger and protection. Its regular return gave comfort. Its changes suggested death and renewal. It was one of the first heavenly bodies that taught people to expect pattern in the sky. The moon's connection to tides is physically real, though ancient explanations varied. The gravitational pull of the moon, together with the sun, helps produce Earth's ocean tides. Coastal peoples knew the timing of tides through direct experience long before modern gravitational theory. They did not need Newton's mathematics to know that the sea came and went according to patterns. In places where tides mattered for fishing, travel, shellfish gathering, harbor access, and survival, the moon's cycle was not only beautiful, it was practical. Ancient skywatching was therefore not a hobby in the modern sense. It belonged to farming, ritual, navigation, kingship, and social order. People watched horizons, counted nights, noted seasons, built monuments, created calendars, and attached stories to repeating patterns. They did this with naked eyes, memory stones, strings, marks, chants, priests, elders, and patient attention. The moon was one of the simplest and most powerful objects in this older science of watching. It is important not to flatten all ancient lunar traditions into one story. The moon meant different things in Mesopotamia, Egypt, China, Mesoamerica, Greece, Rome, India, indigenous North America, Polynesia, and many other worlds. Some traditions tracked lunar months with great precision. Some connected the moon to gods or royal calendars. Some used lunar observation alongside solar, stellar, or seasonal systems. The differences matter. But behind the differences was a shared human fact. The moon was visible, changing, and impossible to ignore. Moon also belonged to childhood. Long before a person could understand distance, gravity, geology, or orbital mechanics, they could look up and know the moon. It followed travelers. It appeared through windows. It hung above fields and rooftops. It made night feel watched. It became one of the first cosmic objects that a human child could name. This is why the scientific history of the moon does not replace the older human history. The moon did not stop being poetic when it became astronomical. It did not stop being symbolic when it became a physical world. The telescope added mountains and craters. Rockets added footprints and flags. Spacecraft added samples and measurements. But beneath all of that, the moon remained the old light in the sky, changing patiently above human lives. The human story of the moon begins in that older silence. People standing under a night sky, watching a pale disk change shape, learning to count time from its return, fearing its eclipse, following its light, and telling stories about why the nearest world beyond Earth seemed to know the rhythm of human memory. The telescope turns the moon into a world. For most of human history, the moon was a visible mystery. People could see its phases and markings, but they could not clearly see its mountains, crater walls, valleys, or rough surface. To the naked eye, the moon looked like a bright disk marked by darker patches. It could be measured, predicted, worshipped, feared, and named, but it could not yet be visited by sight. The telescope changed that. In the early 17th century, telescopic astronomy began to transform the heavens. Galileo Galilei was one of the key figures in this transformation. When he turned a telescope toward the moon, he saw shadows, irregular boundaries between light and dark, bright highlands and dark lowlands. These observations suggested mountains and valleys. The moon was not a perfectly smooth celestial sphere. It was a rugged world. That was a profound change in meaning. In older Aristotelian cosmology, the heavens were often imagined as more perfect than the earthly realm. The moon, seen through a telescope, looked less like a polished lamp and more like a landscape. It had relief. It had roughness. It had places where sunlight struck high ground while nearby areas remained dark. The same principles of light and shadow that revealed mountains on Earth could reveal mountains on the moon. The telescope did not make the moon understandable all at once. Early instruments were limited. Lenses were imperfect. Drawings varied. Observers disagreed. The moon's changing phases meant different features were visible under different lighting. Still, the direction of thought had changed. The moon was becoming a place that could be mapped. Early lunar maps turned the moon into a geography. Observers drew dark plains, bright regions, craters, rays, and highlands. They gave features names. The dark regions came to be called Maria, meaning seas, because early observers imagined that they might be bodies of water. Names such as Mare Tranquillitatis, the Sea of Tranquility, still preserve this old interpretation. The names survived even after science showed that these were not seas at all. The Maria are broad basalt plains formed by ancient volcanic lava flows. They are darker than the highlands because of their composition and surface properties. Many formed billions of years ago when large impact basins were later flooded by lava from the moon's interior. To the naked eye, they make the familiar face-like patterns that people have seen for millennia. To science, they record the moon's volcanic past and the violent history of impacts that shaped it. The bright highlands are generally older and more heavily cratered. They preserve a record of impacts from the early solar system. When telescopes improved, the moon began to appear not as a symbol of smooth heavenly order, but as a battered archive. Craters overlapped other craters. Bright rays spread from younger impacts. Mountain rings enclosed ancient basins. The moon had a surface that told a story, even before anyone knew how to read it fully. The telescope also changed the relationship between imagination and evidence. Before telescopes, the moon could be a realm of gods, spirits, stories, or omens. After telescopes, it could still inspire imagination, but now that imagination had to contend with visible terrain. artists and writers began to imagine voyages to the moon in more concrete ways. Philosophers and scientists debated whether the moon might have inhabitants, air, water, vegetation, or seas. Some ideas were wrong, but they show how the moon was moving from mythic distance toward physical speculation. Lunar mapping improved over centuries. Astronomers such as Johannes Hevelius, Giovanni Battista Riccioli, Francesco Maria Grimaldi, and later observers helped create naming systems and increasingly detailed maps. Riccioli and Grimaldi's 17th century map influenced many of the names still used for lunar features. Mountains, craters, seas, bays, and valleys turned the moon into a named world. Naming is powerful. A named place feels closer than an unnamed light. Photography later transformed lunar study again. In the 19th century, photographers began capturing the moon through telescopes. Photographs reduced some of the subjectivity of hand-drawn maps, though early lunar photography had its own limitations. The moon became an object of chemical plates, observatory domes, exposure times, and scientific comparison. Each advance in optical technology made the nearest world more detailed and less dreamlike. At the same time, the moon remained unreachable. The telescope could pull it close to the eye, but not to the hand. Astronomers could map craters, but not walk across them. They could measure shadows, but not touch the dust. They could debate whether volcanic eruptions or impacts made the craters, but they could not yet bring samples home. The moon had become visible as a world before it became accessible as a destination. This period also deepened understanding of the moon's motion. Its orbit, phases, eclipses, and relation to tides became part of celestial mechanics. Isaac Newton's work on gravity helped explain how the same force that pulled objects toward Earth also governed the motion of the moon. The moon was no longer separate from earthly physics. It belonged to the same universe of force, mass, motion, and mathematics. That realization was as important as any telescope image. The moon was not a magical exception. It was not a lamp attached to a perfect shell. It was a body moving through space under gravitational law. It affected Earth, and Earth affected it. The tides, the orbit, the phases, and eclipses could be understood through geometry and physics. Wonder did not vanish. It changed form. By the early 20th century, the moon was both familiar and remote. It had been mapped, photographed, named, measured, and imagined in science fiction. It had become a target for rocketry theorists, who understood that reaching another world would require escape velocity, propulsion, guidance, life support, and immense engineering. The moon was no longer just the nearest light in the night sky. It was the nearest possible destination. The telescope era, therefore, marks a turning point in the human story of the moon. The moon became a landscape before it became a landing site. It became a map before it became a mission. It became a world in the human mind before human feet ever touched it. To imagine that change, picture an old observatory in cold night air. A telescope points through a slit in the dome. On a table nearby lie sketches of craters and dark plains. Outside, the moon shines as it always has. Inside, human understanding has shifted. The light in the sky has become terrain, Apollo and the human footprints in the dust. By the middle of the 20th century, the moon was no longer only a subject of calendars, telescopes, maps, or dreams. It had become a target of machines. Rockets rose from Earth carrying instruments, animals, and eventually human beings. The old light in the sky was drawn into the politics and engineering of the Cold War. The moon became a destination, not only because it was close, but because it was difficult enough to prove power. The space race between the United States and the Soviet Union changed the moon's meaning. It became a symbol of technological capability, national prestige, military-adjacent rocketry, scientific ambition, and ideological competition. The Soviet Union achieved many early firsts: the first artificial satellite, the first human in space, the first spacecraft to impact the moon, the first images of the moon's far side, and the first soft landing by a robotic probe. The United States responded with escalating commitment, culminating in the Apollo program. Apollo was not just one mission. It was a vast system of research, manufacturing, testing, failure, risk, training, mathematics, industry, and human judgment. It involved the Saturn V rocket, the command and service module, the lunar module, spacesuits, computers, mission control, tracking networks, geology training, recovery ships, and thousands upon thousands of people whose names are not widely remembered. The image of one astronaut on a ladder contains the labor of an entire civilization behind it. Apollo 8 in December 1968 was one of the great turning points. It did not land. Instead, Frank Borman, Jim Lovell, and Bill Anders became the first humans to orbit the moon. They saw the lunar far side with human eyes, passed behind the moon out of radio contact, and witnessed Earth rising above the lunar horizon. The Earthrise photograph became one of the most powerful images in human history. It showed Earth as small, bright, blue, and fragile above a gray, lifeless surface. That image changed the direction of awe. For centuries, people looked from Earth to the moon. Apollo 8 allowed people to look, through the astronauts' eyes and camera, from the moon back to Earth. The moon became a mirror, showing humanity its own home from outside. The closest world beyond Earth made Earth itself seem more precious. Apollo 11, in July 1969, brought the first crewed landing. Neil Armstrong and Buzz Aldrin descended in the lunar module Eagle, while Michael Collins orbited above in the command module Columbia. The landing was not smooth in any simple sense. Alarms sounded. Fuel margins became tight. Armstrong guided the craft away from rough terrain. When Eagle landed in the Sea of Tranquility, the moon changed again. It was no longer only seen, mapped, orbited, or photographed. It had been touched. The first moonwalk was short compared with later missions, but historically enormous. Armstrong stepped onto the surface. Aldrin followed. They planted instruments, collected samples, took photographs, and left footprints in fine lunar dust. They also left behind objects, including a plaque and memorial items. The surface was gray, powdery, bright in sunlight, and black in shadow. The sky was dark even in daytime because the moon has no substantial atmosphere to scatter sunlight like Earth's sky does. The words and images from Apollo 11 became global memory. The ladder, the bootprint, the flag, the lunar module, the Earth hanging in darkness, the astronauts moving awkwardly in reduced gravity. But Apollo 11 was not the end of lunar exploration. It was the opening of a short but intense period of human surface science. Apollo 12 landed near the robotic Surveyor 3 spacecraft, showing that precise landing was possible. Apollo 13 was intended to land, but an oxygen tank explosion forced the crew to abandon the landing, circle the moon, and return safely to Earth through extraordinary teamwork and improvisation. Apollo 14 returned astronauts to the surface. Apollo 15 introduced the lunar roving vehicle, allowing astronauts to travel farther from the lunar module. Apollo 16 explored the lunar highlands. Apollo 17, in December 1972, became the final Apollo mission to land humans on the moon. Apollo 17 was especially important scientifically. Its crew included Harrison Schmitt, a trained geologist, along with Eugene Cernan and Ronald Evans. Cernan and Schmitt conducted 3 moonwalks and collected a large quantity of lunar samples. When they left, Cernan became the last human to walk on the moon. His footprints remained, not because they were guarded, but because the moon has no wind or rain to erase them quickly. The Apollo samples transformed lunar science. Moon rocks and soil helped reveal the age of lunar surfaces, the volcanic nature of the Maria, the impact history of the moon, and clues about the moon's origin. They showed that the moon was not made of cheese, crystal, or divine light, but of minerals, basalt, breccia, anorthosite, glass beads, and dust shaped by impacts and ancient heat. The samples made the moon physical in a way no photograph could. Apollo also left equipment behind: experiments, descent stages, rovers, tools, cameras, and human waste. The moon became an archaeological site of the space age. The landing sites are not only scientific places, they are human heritage sites. They mark the moment when a species born on one world briefly stood on another. But Apollo ended quickly. After Apollo 17, no human returned to the moon for decades. Budget pressures, political priorities, public attention, and the immense cost of lunar missions shifted the United States away from crewed lunar landings. The moon, once reached, became distant again. It remained above Earth as before, but now with a strange new status: visited, sampled, photographed, and abandoned. The end of Apollo gave the moon a kind of unfinished feeling. Humanity had proven it could go there, but not that it knew how to stay. The program had been extraordinary, but also specific to its time. Cold War urgency, national commitment, concentrated funding, and a willingness to accept great risk. Once that urgency faded, the moon returned to patience. The Apollo story should not be reduced to triumph alone. It included fatal risk, especially remembered through the Apollo 1 fire, which killed Gus Grissom, Ed White, and Roger Chaffee during a ground test in 1967. It included political pressure, military technology, environmental questions, social criticism, and the fact that many people on Earth wondered why such resources were spent on the moon while human suffering remained below. These questions were real then and remain real in different forms now. Yet Apollo also expanded human imagination. It gave Earth a new portrait of itself. It brought another world into geology labs. It proved that humans could travel beyond low Earth orbit, navigate through deep space, descend to another surface, work there, and return. It made the moon both less mysterious and more profound. The footprints in the dust are still there, slowly altered by micrometeorite impacts and space weathering, but not erased by weather. They are among the quietest monuments humans have ever made. No stone was carved. No temple was built. A boot pressed into regolith, and the mark remained. That is the heart of Apollo in the human story of the moon. For thousands of years, the moon shaped human time from above. Then, for a few brief years, humans crossed the distance and left time written in dust. The real moon, stone, silence, craters, and ice. The moon of myth, calendar, telescope, and Apollo is also a real physical world. It is not simply a symbol in the sky or a stage for human achievement. It is a body of stone, dust, glass, metal, shadow, sunlight, heat, cold, craters, basins, mountains, and ancient volcanic plains. To understand the moon as a world, we have to remove many familiar Earth habits from our imagination. The moon has no breathable atmosphere. It has only an extremely thin exosphere, far too sparse to behave like Earth's air. There is no blue sky on the lunar surface. There are no clouds, rainstorms, oceans, rivers, forests, or winds like Earth's. The sun can blaze harshly over one part of the surface, while nearby shadows remain black and cold. Without an atmosphere to scatter light, the contrast between sunlight and darkness is severe. There is no Earth-like weather to soften the landscape. Craters can remain recognizable for immense spans of time. Footprints can persist far longer than they would on Earth. Rocks do not erode through rain and rivers. Instead, the lunar surface is shaped by impacts, temperature extremes, radiation, solar wind, and the slow grinding of micrometeorites. The moon changes, but on terms very different from Earth. The surface layer is called regolith. It is not soil in the earthly sense, because it has no organic life, no worms, no roots, and no living ecosystem. It is a broken layer of dust, glassy fragments, mineral grains, and small rocks produced by billions of years of impacts and surface processing. Apollo astronauts found that lunar dust was fine, clingy, abrasive, and difficult. It stuck to suits and equipment. It smelled unusual when brought into the lunar module, likely because fresh dust reacted after entering the cabin environment. The moon's bright highlands are ancient crust, heavily battered by impacts. They contain rocks such as anorthosite, suggesting early differentiation when the young moon may have had a magma ocean. As that molten surface cooled, lighter minerals floated upward to form crust. This idea helps explain the composition of the highlands, though details of lunar formation and early evolution remain active areas of research. The dark maria are younger basalt plains created by ancient lava flows. They are mostly found on the near side of the moon, the side that always faces Earth because the moon is tidally locked. Tidal locking means the moon rotates once in about the same time it takes to orbit Earth, so the same hemisphere generally faces us. The far side is not permanently dark. It receives sunlight just like the near side. It is far because we do not see it from Earth. The far side looks different. It has fewer large maria and is more heavily dominated by highlands and craters. Robotic spacecraft first revealed it. The phrase dark side of the moon is therefore misleading if it means a side that never sees sunlight. The far side has day and night. It was dark to human knowledge before spacecraft, not dark to the sun. Craters are among the moon's most important features. Some are small bowl-shaped pits. Others are immense basins hundreds or thousands of kilometers across. The largest impacts reshaped the moon's crust and created basins later filled by lava. Younger craters can have bright ray systems where impact ejecta spread across the surface. By counting craters and comparing surfaces, scientists can estimate relative ages. Older surfaces generally have more craters. The moon is a record of the early solar system because it preserves impact history better than Earth. Earth has plate tectonics, whether oceans, vegetation, erosion, and active geology that recycle or hide much of its oldest surface. The moon is quieter. Its scars remain. Studying the moon helps scientists understand bombardment, planetary crusts, volcanic history, and the environment in which Earth itself developed. The origin of the moon is still studied, but the leading model is the giant impact hypothesis. According to this idea, a Mars-sized body, often called Theia in scientific discussion, struck the early Earth more than 4 billion years ago. Debris from that impact eventually gathered in orbit and formed the moon. This model helps explain several features of the Earth-Moon system, though scientists continue refining the details. The moon's birth was not gentle. It likely began in violence on a planetary scale. The moon also stabilizes Earth in important ways. Its gravity contributes to tides, and the Earth-Moon relationship affects Earth's axial stability over long timescales. The moon is not merely a companion light. It is part of Earth's physical system. Life on Earth evolved under a sky with a large nearby moon. Tides, calendars, coastal ecosystems, and human imagination all developed in its presence. For decades after Apollo, many scientists thought the moon was extremely dry. Early analysis of Apollo samples seemed to support a dry moon view. Later discoveries changed that understanding. Water is present on the moon in more than one form and setting, though though it is not like Earth's water. It is not flowing in rivers or filling lakes. It is sparse, difficult, chemically and physically varied, and unevenly distributed. Permanently shadowed regions near the lunar poles are especially important because the moon's axis is only slightly tilted. Some deep crater floors near the poles may remain in shadow for extremely long periods. These cold traps can preserve water ice and other volatile compounds delivered by comets, asteroids, solar wind interactions, or other processes. Such ice is scientifically valuable because it may preserve a history of materials delivered to the inner solar system. It is also strategically interesting because water could potentially support future exploration if it can be accessed and processed. Water molecules have also been detected on sunlit lunar surfaces. NASA's SOFIA Observatory confirmed water molecules in Clavius crater in 2020, suggesting that water is not limited only to permanently shadowed places. Later mapping helped show patterns in water distribution, including toward the lunar south polar region. But this does not mean the moon is wet in any ordinary sense. The amounts are small, the forms are complex, and practical use remains difficult. The lunar south pole has become especially important for future exploration because it combines scientific interest with possible resource value. Peaks and ridges near the poles may receive periods of useful sunlight, while nearby permanently shadowed regions may contain ice. That combination makes the region attractive for robotic missions and future human planning. But it is also challenging terrain. Low sun angles, extreme shadows, communication issues, cold traps, rough surfaces, and uncertain ice distribution. The moon is also seismically quiet compared with Earth, but not completely inactive. Apollo seismometers detected moonquakes, including deep moonquakes linked to tidal stresses, shallow moonquakes, and impacts. Without plate tectonics like Earth's, lunar geology is different. But the moon is not simply dead in a poetic sense. It has history, structure, stress, and response. The moon's silence is therefore not emptiness. It is a different kind of archive. Every crater, plain, boulder field, ray system, lava flow, and shadowed basin belongs to a record older than human civilization. When astronauts walked there, they were stepping onto a surface shaped by billions of years before language, agriculture, temples, cities, or telescopes. This is why the moon remains scientifically powerful after all the photographs. A picture can make it familiar, but the reality is stranger. It is close, but alien, bright, but airless, visited, but barely explored, quiet, but full of evidence. It has no forests, but preserves the history of impacts. It has no oceans, but carries the old names of seas. It has no weather, but holds human footprints. It has little water, but enough to reshape future plans. The real moon is not less mysterious than the mythic moon. It is mysterious in a different way. A scarred companion world born from planetary violence, locked in orbit with Earth, reflecting sunlight into human eyes, and waiting with its craters, ice, dust and silence. Artemis and the future of Earth's closest world. After Apollo, the moon did not leave human imagination, but human footsteps did not return. Robotic missions continued. Orbiters mapped the surface in new detail. Probes studied gravity, composition, topography, radiation, and possible ice. Other nations sent spacecraft. The moon became global again, no longer only an American-Soviet Cold War prize. It became a scientific target, a technological test ground, a heritage landscape, and a possible future frontier. The Artemis program is NASA's current effort to return humans to deep space around the moon and eventually to the lunar surface. It is not Apollo repeated in the same form. Apollo was built around a race to land quickly and prove capability. Artemis is framed around sustained exploration, international partnerships, commercial systems, long-term infrastructure, lunar South Pole science, and preparation for future missions beyond the moon, including Mars. Artemis, I was the uncrewed test flight of the Space Launch System rocket and Orion spacecraft. It launched in November 2022, traveled around the moon, tested systems in deep space, and returned Orion safely to Earth in December 2022. The mission did not carry astronauts, but it was crucial because crewed exploration depends on proving launch, navigation, propulsion, communication, heat shield performance, recovery, and deep space operations before people are placed inside the spacecraft. Artemis, I showed that the new system could send Orion beyond the moon and bring it home. That matters because the hardest part of lunar exploration is not only reaching the moon, it is doing so repeatedly, safely, with enough confidence to build a program rather than a single demonstration. Artemis II is the first crewed Artemis flight. NASA has described it as a crewed lunar flyby, carrying NASA astronauts Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. The mission is designed to send humans around the moon for the first time since Apollo, testing Orion's life support, crew operations, navigation, communications, and overall performance with people aboard. It represents a bridge between Apollo memory and a new generation of lunar exploration. The Artemis sequence has changed over time, and that is important for accuracy. Earlier public expectations often described Artemis III as the first crewed Artemis lunar landing. NASA's current framing has shifted. Artemis III is now described as a low Earth orbit rendezvous and docking mission intended to test integrated operations between Orion and one or both commercial human landing systems from SpaceX and Blue Origin. In other words, Artemis III is currently planned as a systems test needed for later landings, not the landing itself. This is a useful reminder that spaceflight plans are not fixed monuments. They change when engineering, budgets, safety reviews, contractors, vehicles, politics, and timelines change. A lunar program is not only a story of rockets rising. It is a story of schedules slipping, systems being redesigned, tests revealing problems, and mission goals being adjusted. Exploration is not a straight line. It is a long negotiation with reality. NASA's current planning places the first Artemis crewed lunar surface return in a later mission, with target dates that should be treated cautiously rather than as guarantees. Future Artemis surface missions are expected to involve Orion, commercial lunar landers, new spacesuits, and operations near the lunar South Pole. The South Pole matters because of its permanently shadowed regions, possible water ice, and unusual lighting conditions. But it is also difficult terrain. The idea of using lunar water is often presented too simply. Water could, in principle, support drinking water, oxygen production, radiation shielding, agriculture experiments, or rocket propellant if split into hydrogen and oxygen. But locating, extracting, processing, storing, and using lunar water at meaningful scale is extremely hard. Ice may be patchy, mixed with regolith, trapped in dangerous shadows, or present in forms that are not easy to mine. The moon does not hand resources to humans. It makes them work for every gram. Artemis also includes the idea of Gateway, a planned small space station in lunar orbit involving NASA and international partners. Gateway is intended to support future lunar operations, science, staging, and possibly Mars preparation. Like other future infrastructure, it should be described carefully because schedules and configurations can change. But the broader idea is clear. The future moon is being imagined not as one landing site, but as a network of spacecraft, orbiting platforms, landers, rovers, habitats, suits, power systems, communications, and supply chains. Commercial companies now play a larger role in lunar plans than they did during Apollo. NASA contracts with companies for landers, cargo delivery, technologies, and services. This changes the character of exploration. It adds flexibility and innovation, but also complexity, dependency, and new kinds of risk. The moon is becoming a place where governments, companies, scientists, engineers, and international partners all have overlapping ambitions. Other countries are also active. China has conducted successful Chang lunar missions, including sample return. India has landed near the lunar South Polar region with Chandrayaan-3. Japan, the European Space Agency, Russia, private companies, and others have pursued or planned lunar missions with varying degrees of success. The moon is no longer the private stage of two superpowers. It is becoming a shared and contested space of science, prestige, technology, and future possibility. This raises questions that Apollo did not fully answer. Who protects lunar heritage sites? Who has rights to use lunar resources? How should nations avoid harmful interference with one another? What counts as responsible exploration? How do we preserve scientifically valuable regions? How do we prevent the moon from becoming only another place of extraction, competition, and discarded machinery? The Outer Space Treaty of 1967 says that outer space, including the moon and other celestial bodies, is not subject to national appropriation by claims of sovereignty. But the practical details of resource use, safety zones, commercial activity, and long-term presence are still developing through agreements, national laws, norms, and debates. The moon is close enough to tempt ownership and distant enough to reveal how fragile ownership language can be beyond Earth. For asleep in class, the future moon should not be imagined as a glittering science fiction city. A more honest image is quieter. A small habitat near a harsh horizon, solar arrays catching low light, astronauts moving carefully in dust, robotic rovers entering shadow, Earth hanging above the black sky, and old Apollo artifacts sitting elsewhere like relics from the first age of lunar travel. The future moon may become a place of science. Telescopes on the far side, geology at the poles, samples from ancient basins, studies of solar wind, radiation, dust, and planetary history. It may become a training ground for deeper space missions. It may become a place of national prestige and commercial ambition. It may remain, for a long time, mostly unreachable to ordinary human beings, present in images and stories more than footsteps. But even if humans build nothing permanent there, the moon has already changed us. It taught early people to count time. It shaped myths. It challenged old cosmologies. It helped create modern astronomy. It gave Earth tides and night light. It became the first world humans reached beyond their own. It returned our gaze back to Earth. It became both a place and a mirror. The human story of the moon is therefore unfinished. It began before writing, continued through temples and calendars, passed through telescopes and maps, rose on rockets, paused in dust, and now resumes through Artemis and global lunar exploration. The moon has been watched longer than any empire has lasted. It has outlived every language used to name it. It has shone over every human civilization. When we look at the moon now, we are seeing many histories at once. We see the ancient calendar, the mythic light, the telescope's landscape, the Apollo footprint, the scientific archive, the shadowed ice, the planned return, and the unanswered future. It is close, but not familiar. Known, but not finished. Visited, but not possessed. Earth's closest world remains what it has always been, a quiet companion above us, holding the memory of where we have been and the question of where we might go next.